Welcome to this deep dive into RoboFlamingo, a groundbreaking vision-language foundation model that's transforming how robots learn to manipulate objects. If you've ever wondered how we can teach robots to understand human instructions and perform complex tasks, this paper has some fascinating answers. Imagine telling a robot to pick up a red block and put it in a drawer, and the robot actually understanding and executing that command. Published by researchers from ByteDance Research, Tsinghua University, and other leading institutions, RoboFlamingo represents a significant leap forward in language-conditioned robot manipulation. The key innovation is adapting powerful vision-language models trained on internet-scale data to directly control robots without requiring massive amounts of robot-specific training data. The beauty of RoboFlamingo lies in its elegant simplicity. While previous approaches either required expensive co-training on both web data and robotics data, or relied on complex hierarchical planning systems, RoboFlamingo takes a different path. It builds upon OpenFlamingo, an open-source vision language model, and fine-tunes it specifically for robotics tasks. Think of it like taking a person who's read thousands of books and watched millions of videos, and then giving them just a bit of hands-on training to apply that knowledge to physical tasks. The model already understands what objects are, what actions mean, and how language relates to visual concepts. It just needs to learn how to translate that understanding into precise robot movements. The architecture consists of two main components. The Flamingo backbone handles vision language understanding, while the policy head translates that understanding into robot actions. The vision encoder uses a vision transformer to process images from multiple camera angles, breaking each image into patches and encoding them into feature vectors. Here's where it gets interesting. A perceiver resampler compresses hundreds of visual tokens down to a fixed number, like 64 tokens, without losing important information. These compressed visual features then flow into the feature fusion decoder, where language instructions and visual tokens interact through cross-attention. The language tokens act as queries about the visual scene, while the visual tokens provide answers. This creates a joint vision language representation that captures both what the robot sees and what it needs to do. The policy head converts this representation into actual robot commands. RoboFlamingo experiments with several architectures, from simple multi-layer perceptrons to LSTM networks and GPT-style transformers. Temporal modeling proves crucial, as robot manipulation requires understanding what happened before, not just what's happening in the current moment. The policy head outputs a 7-degree of freedom action, 3 dimensions for position change, 3 for rotation change, and 1 for gripper state. Training is remarkably efficient. The researchers use imitation learning from expert demonstrations, but crucially, only fine-tune specific components. The vision encoder and core language model remain frozen, preserving all the knowledge from web-scale data. Only the perceiver resampler, cross-attention layers, and policy head are trained. This reduces trainable parameters to about 1 billion, making training much faster and requiring less data. The experimental results are truly impressive. Evaluated on Calvin, a benchmark for long-horizon manipulation tasks requiring robots to complete sequences of up to 5 tasks, RoboFlamingo achieved 96.4% success on the first task and completed an average of 4.09 tasks in sequence. The previous state-of-the-art method, HULC, achieved only 3.06 tasks on average. That's more than a 30% improvement using only 1% of the available data. The zero-shot generalization capabilities are particularly exciting. When trained on 3 environments and tested on a completely different 4th environment with novel visual contexts, RoboFlamingo completed 2.48 tasks on average, while HULC managed only 0.67 tasks. This shows that vision language pre-training really helps the model understand and adapt to new scenarios. The researchers also tested language generalization using 50 different phrasings for each instruction generated by GPT-4. Even with this linguistic variation, RoboFlamingo maintained strong performance. Let's examine what makes RoboFlamingo different from previous approaches. Traditional methods train policies from scratch, using only robot data, requiring enormous amounts of task-specific demonstrations. Other approaches use large language models as high-level planners, like SayCan and PaLM-E, which generate plans executed by separate controllers. Then there's RT-2, Google's robotics transformer, which also adapts vision language models but requires expensive co-training on massive web and robot datasets using proprietary models. RoboFlamingo's key insight is you don't need to retrain on web data. The pre-trained model already has rich visual and linguistic knowledge. You just need to add a policy head and fine-tune connection layers on robot data. The ablation studies reveal fascinating insights. History information is crucial, as policies using only current observations perform poorly. Vision language pre-training is essential, with models trained from scratch collapsing almost entirely. Model size matters when data is scarce, with larger models showing better sample efficiency. Instruction tuning also helps, suggesting that instruction-following capabilities transfer from language tasks to embodied control. One clever aspect is the potential for open-loop control. Instead of predicting one action at a time, RoboFlamingo can predict action sequences all at once, then execute them without running the model again. This significantly reduces computational requirements during deployment, making it feasible on less powerful hardware. The researchers explored whether fine-tuning causes catastrophic forgetting of original vision language capabilities. Testing on image captioning and visual question answering showed performance drops after robot fine-tuning. Co-training, mixing robot data with vision language data, preserved more original capabilities, though with slight decreases in robot performance. This reveals an interesting trade-off between specialization and retention of general abilities. Practically, RoboFlamingo demonstrates that building capable robot systems doesn't require massive resources. The entire framework trains on a single server with 8 NVIDIA A100 GPUs in just a few days. This accessibility is crucial for democratizing robot learning research. The open-source framework based on publicly available components enables researchers to build upon and improve the work. The work highlights important research directions. A key limitation is that RoboFlamingo is only tested in simulation. Real-world deployment introduces challenges like sensor noise and unexpected physical interactions. Integrating multimodal sensory input, including force torque and tactile sensors, could improve manipulation of delicate objects. Continual learning remains an open question, as robots encounter new tasks without forgetting previous skills. From a broader perspective, RoboFlamingo represents progress toward foundation models for robotics. Just as GPT provides general-purpose foundations for language tasks, we need similar foundations for embodied intelligence. RoboFlamingo shows that vision language models pre-trained on internet data can serve this role. The model's generalization to unseen objects, environments, and language phrasings suggest it has learned meaningful abstractions about manipulation. However, there's still a significant gap between the 34 tasks in Calvin and the open-ended diversity of real-world manipulation scenarios. In conclusion, RoboFlamingo makes several important contributions. It demonstrates that open-source vision language models can be effectively adapted to robot control through simple architectural additions. It achieves state-of-the-art performance while being data efficient and computationally accessible. It shows that vision language pre-training provides crucial inductive biases enabling generalization, and it provides an open framework that researchers can build upon. The work elegantly bridges the gap between semantic knowledge in large-scale vision language models and precise motor skills required for robot manipulation. As we continue to see larger and more capable foundation models, approaches like RoboFlamingo will likely play a central role in creating robots that can understand and execute a wide range of human instructions. Thank you so much for watching this deep dive into RoboFlamingo. If you found this breakdown helpful, please hit that like button and subscribe to the channel. If you have thoughts about where robot learning should go next, drop a comment below. Until next time, keep exploring the frontiers of AI and robotics.